Okay, so if everyone can hear me. Right. Okay. So today I want to talk a little bit about about our active vision. So our next phase of this course is active vision. This is going to be our last lab in this course, be the active vision. And active vision is where there's vision that sends something out and receives something back. You know, like radar vision, that kind of thing is active vision. So what we're going to do is I'll provide you with some data, and we're going to look at radar data, for example. And so we collected some radar data pertaining to ice safety, and that sort of thing. If I share my screen, let me share the screen here. Well, first I'll just say we have a radar set. Actually, I can even show you what. I'll just switch over to the chalkboard camera, and close the aperture down a little bit so that it isn't so overexposed. And so over on the chalkboard, we've got a radar set. So we built a radar system, and we use that to collect some data. So the radar system has in-phase quadrature. There's antenna, a transmit antenna, receive antenna, and it transmits radio waves and measures the bouncing back of the radio waves. Radar, LiDAR, sonar, and so on are examples of active vision. This is a radar set here. You can see right here is this radar horn that collimates or directs the energy in this direction. So the radar wave goes to some subject matter or object in the real world, and the radar wave goes out here, and like this, it comes out of this antenna and bounces off of some object and then comes back. And if we take that signal, radar signal, and it's received here, and we have a modulator or multiplier mixer. In radio, mixing means multiplying. So in audio, if you're a disc jockey and you have two record players, mixers means adding. A mixer is a device that adds some things together. In radio engineers usually think of a mixer as something that multiplies signals together. So the result is sum and difference frequency components. In the frequency domain, you have the sum and difference frequencies appearing when you multiply two things together. So if I multiply cos omega t here with something cos omega t minus kx, and here we're multiplying that signal together, and then we're going to have a sum of difference frequency, and then we low-pass filter the result, and then out comes the Doppler shifted signal. And so what we have here is there's some subject matter here, let's say, and then these radio waves bounce back off the subject matter into this antenna here. And I have this oscilloscope here showing the baseband Doppler shift signal. And if I just zoom in a little bit on that oscilloscope screen, you can see this oscilloscope was made in the 1960s. It's an oscilloscope. It was actually based on something called the tummy TV. Sony made something called the tummy TV, which shows the television that you wear around your tummy. So it has a little shoulder strap that you can hang it over your neck, so it hangs in front of your tummy, and then you can look down at the screen to watch the TV or look at the oscilloscope. And so this is perhaps one of the first wearable oscilloscopes. It runs on 12 volts, it's battery operated. And I've zoomed in close to the screen here so you can see it. Now as I move my hand there, if I move my hand slowly, you can see that the Doppler shift is relatively slow. As I move my hand a little faster, the Doppler shift is faster. And if I move my hand even faster, the Doppler shift is even. There you can see that on the screen there. And so now you can see that waveform here is coming from the movement here. So again, you see if I move my hand relatively slowly, you can see that Doppler shift is relatively low frequencies. Moving really slow. And as I move really slow, see the voltage increases and decreases. And the movement in proportion to the speed of light, so that the ratio between the speed of my hand and the speed of light is the same as the ratio between the received signal and the 24.36 gigahertz that's coming out. So the fraction of my speed with respect to the speed of light is thus the fraction of the frequency with respect to the frequency of the radar, which is transmitting at 24.36 gigahertz. And thus we have a simple radar that can look out at ice fragments and understand and see and understand the ice that's moving around in the lake, for example, and try and detect ice fragments that are dangerous to our ship that we might collide against. If you're on a vessel moving through the ice, through the water, you could hit some ice, and even if your vessel is unsinkable like the Titanic, it might hit a piece of ice and still sink. So we want to be able to see the piece of ice and not crash into it. And so you can see as I move faster here, it's faster. And if I take a piece of metal here, move this piece of metal here, you'll see waveform on the oscilloscope corresponding to the movement. It's very slow movement. Again, I'm moving this piece very, very slow. Waveform goes up and down relatively slow. When I move it a little bit faster, it's a little bit faster, and so on, depending on the time base. If I slow the time base down over like that, you see that waveform more. Moderate speed versus when I pick it up to a higher speed, you can see the waveform on the screen. I'll just again so that everybody can see it. There it is. If I'm just moving really slow, really low frequency, and when I move it faster, if I move really fast, you can see these higher frequency components coming back to the radar. And the nice thing about this radar is that it produces a complex valued signal. There's a real and imaginary part. So if I plot both of those traces on the oscillograph, we'll see the two signals there. And if I plot real versus imaginary as a XY plot, then what we see, let me just turn on my light here. Open up the aperture a little bit, maybe. So yeah, that's the thing is with a higher speed as the objects move towards the radar, you get a higher frequency Doppler shift. So that's, we can take those signals coming back, and when they're chirping or changing in pitch, that's a signature that's indicative of accelerating objects. So if our boat's moving at a constant speed, there'll be a constant sea clutter or lake clutter or whatever background. And then of course there's objects that are moving, that are stationary, and there's the waves that are accelerating a little bit, but then the ice has a unique appearance as it's, you know, a single or a small number of objects, a small number of pieces of ice that are moving at these well-defined frequencies, maybe one or two pieces that are moving. Each of them has a chirplet component. So with the chirplet transform, we can resolve it into these different components and see each of the chirp functions. So now let's take a look at some examples. I'm going to share my screen here. Screen 2 is this screen. So we're going to get some feedback for a moment until I switch to here. And then this is, we did this fun little test for sensing of ice safety. This is at Echo Beach. It's a nice little beach at Ontario Place. There's even a song about this beach, you know, far away in time, Echo Beach. And it's not a great swimming beach because Bricatine Cove, where the water is not circulating that much, so it's not totally open water. So as a result, the water's maybe not quite as clean as the regular beach we swim at Ontario Place on the other side on the West Island. This is on the East Island. And so the water's actually better on the West Island. Ontario Place has a couple of different islands, and in between there's a little island, we call it Budweiser Island, where the Budweiser stage is. And so those islands are maybe not as nice and clean, but there's a nice view of the city. And here we have one of our good friends deliberately breaking through the ice just for fun. So he jumped up and down on the ice to punch through it. But ordinarily, you know, when you're walking on the ice, you'll hear it go clicking or clacking, and it can suddenly fracture. You can suddenly fall through the ice without warning. So of course, if you're walking on the ice, you want to be wearing, you know, at least maybe a nice neoprene suit, or if you've had lots of experience ice swimming and you're prepared to swim. So normally we'll put on our bathing suits and, you know, walk across the ice, expecting that sooner or later we're going to fall through. You got to be careful that you don't scratch up on the pieces of ice as you drop through. The rubber neoprene suit helps a little bit protect from that. And he's wearing a life jacket so that when he does drop through, you get a little bit of buoyancy. And the other risk, of course, is you can get washed away. So if there's currents underneath the ice, you know, you might jump through the ice and then just disappear and not be found. So you have to really be careful knowing what the currents are. So you really, really got to focus on safety when you're on ice, because there's a lot of potential risks. So as a result, safety is a really important thing to be aware of. And so radar can help us understand the ice. We can see how thick, well, it's not just a matter of how thick the ice is, but the structure. This is what's called rotten ice here. And rotten ice is when the ice is really thick, but very weak, because it's melted in such a way that it's fractured into little pieces that's invisible. It looks solid, but as you can see, he just lightly jumps on it and drops through. So the ice has gone rotten due to the way that it's formed. It hasn't formed solid. And so this radar set here has you know, some low noise amplifiers, a Gilbert cell, which does multiplication. It's basically a lock-in amplifier, which is designed to operate at the frequencies that we're transmitting at. This radar is 2.5 gigahertz. The other one that I showed you is 24 gigahertz. Some marine radars, a lot of them are around 10 gigahertz or so, is fairly common, like 10.525 gigahertz is a very common marine radar or amateur ham radio frequency that people use. As you can see, there's different properties to the ice here. There's, at the edges of the ice, there's You can see the rotten ice. You can tell it's rotten ice, but when you look at the edge, you can't tell from looking in the middle of it. It looks substantial, but if you look closely at the edge, you can see those characteristic forms of rotten ice. And rotten ice has a beautiful musical sound too. When it breaks up, it sounds almost like chimes when the little pieces of it are rattling around. So if you look on our Swim OP website, you can see lots of sound recordings that we've made of rotten ice. And even we do simultaneous Doppler radar and audio recordings of rotten ice just to kind of understand it better. But you can tell it's rotten ice here when you look at the edges of it and the way that it's formed. So I'm stepping very carefully on the ice here to do a little bit of experiments with moving pieces of it. You'll notice that I'm prepared to swim. I have a life belt on, which is an inflatable life jacket if I need it. And I've got a full neoprene suit on with a double neoprene boots. I've got like a full centimeter of neoprene, and I've got the spikes on the boots to avoid slipping, of course, being careful not to punch through the ice, but also being ready to fall through the ice at any time without warning. And we have an oscilloscope here to look at the XY plot of the radar, and we've got some radar data that we collected here as a complex valued return. There'll be two lists of numbers, the real part and the imaginary part for each data point. And you can plot those as a function of X, Y, and time, X, Y, T, and get an understanding. What we did here in this lower picture is we plotted the real and imaginary parts in green and blue here. We put the axis label. There's a character generator on the swim. It's like a little oscilloscope. Call it a scientific instrument because it happens like outside the box. It's outside of its package or box. It just shows the phenomenology overlaid on top of the reality in which we are placed here. It's quite a nice view of the city skyline from Echo Beach. It is a very beautiful beach for playing beach volleyball and so on, and just enjoying the sunset and watching the Toronto skyline there. Here we have, we swim out from the beach, from Echo Beach. Camera's located on Echo Beach, looking back across Brigantine Cove to the skyline here. And the swim, the sequential wave and printing machine, is moved from left to right. The character generator is labeling the axis ice Q, which Q stands for quality. And the Q factor of the ice is really important in terms of understanding it. We can look at how the Doppler return from the ice can give us some information about it. We can feed that into a machine learning algorithm to try to learn or estimate what we think the quality of the ice will be. We have an ice rink booked for tomorrow, actually, and we're going to do some more testing on an ice rink with the swim mounted to a hockey stick. In this case, we have the swim mounted to a paddle, stand-up paddleboard paddle, so that I can stand on a piece of ice, a fragment of ice, and paddle the ice across, or I can simply walk on the ice and carry the swim across to swim out the phenomenology. Again, in this image in the lower right, you can see here over on the right-hand side of the image, you can see clearly this is rotten ice because you can actually see the way, the characteristic crystalline form of it, and these long crystal pieces that are that go down. Actually, let me just go to. I just got the camera in the lower right corner. So that go down in this little strips of ice. They're long, thin pieces of ice standing together. So we're writing this up now for our WaterHCI conference, Water Human Computer Interface Conference. So we're planning to add this into the WaterHCI. And the WaterHCI conference here, this is our overleaf. We're all using overleaf at the intersection of water, humans, and computers. I designed this little thing here. I took a picture of some water in the shape of a water drop, and then I found a face picture and the oscilloscope representing the technology, so of water, humans, and technology, representing these three in the area of overlap. And so in the area between humans and water, the human can enter the water, i.e. swim, or the water can enter the human, which is to drink, or the two remain separate activities like when you go fishing or sunbathing at the beach and so on. And then likewise, human and technology can interact, as we know with cyborg technology, the way humans and technology interact. Human-computer interface, HCI, is an existing field of human-computer interface. And of course, water and technology can interact. You've got autonomous vessels, autonomous boats, smart buoy. You've got water sensing technology, smart toilets, smart faucets, all these water and technology things. And then at the center here, you've got WaterHCI, which is kind of where all three of these intersect. And so this is just a little summary of our Teach Beach, and then an overview of the talks that we'll be presenting. And this is 6 days from now. So your the final lab will fall conveniently right into that time slot. And so you'll be able to, as part of your lab, join in to this event and participate. If you want to present something or show your work there, it's a perfect opportunity. This is an example of something fun that we designed, a little swim platform, educational swim pier. There's 10 different platforms at 1 meter increments here around a spiral staircase so that you can walk up and jump off of any of these platforms. And let me know if you guys, let me know in the chat, can everybody see the screen and hear? Is the sound good and the screen visibility good? Just let me know in the chat if you can. I think everybody can see and hear what's happening. So there is, for each meter, there's a platform and there's 10 of them. And on each one is labeled the amount of time that you'll be in the air when you jump off of it, and this velocity at which you'll enter the water. And so, for example, the time that you're in the air varies as the square root of the height that you jump from. So if you jump from the 5 meter platform, you will be falling, let's say, if the acceleration to gravity is approximately 10 meters per second here in Toronto, I think it's about 9.806. But let's say if it was approximately 10 meters per second, you're going to be dropping at 10 meters per second squared acceleration. So every second, 10 meters per second more. So you're going to go from 0 to 10 meters per second and averaging about 5. So you're 5 meters. So you're going to be in the air for 1 second if you drop from that 5 meter platform. If you drop from the 10 meter platform, you're going to be in the air for approximately 1.4 seconds, square root of 2 seconds, 1.414, so on. And so each of those numbers, each of those platforms then is labeled with these quantities. And so now it becomes a teach beach, what we call a teach beach. So it's it turns math and physics into fun and frolic so that people can have fun jumping off these platforms. And at the same time, they can learn something about math and physics. Additionally, at each platform, there's a little water jet. So that circular staircase is around a pipe, a steel pole, which is actually a pipe. If you look at how water slides are usually made, they're usually made with pipes. So they're actually hollow. It looks like a steel rod, maybe 1 foot in diameter, 2 feet in diameter, 18 inches in diameter, something like that, a big steel rod going up. And if you look, though, they're actually hollow because they're actually pipes, because the strength mostly comes from the surface. So if you look at buildings, how buildings are made in beams and everything, you see these round or rectangular beams. They're usually hollow because most of the strength comes from the steel that's at the surface. And therefore, it represents an opportunity to pump liquid into the center of this. And in particular, water is pumped up through the center of this pipe, and there's a little hole at each platform through which the water comes out. And at the very top, the water is actually pumped in with 10 meters of head, which is just a little under 1 atmosphere. And it's the exact amount of pressure required to raise water 10 meters. So at the 10 meter platform, the pressure is exactly 0, and the water is just dribbling out of there, neither in or out. So the head is 0. And then if you come down to the 9 meter platform, the water comes out with a head pressure of 1 meter. And if you come down to the 8-meter platform, the water comes up with a head of 2 meters, then 3 at the 7, 4 at the 6, and so on, all the way down to the 1-meter platform where the water comes up with a pressure of 9 meters of head. So you can put your finger over that water jet and attempt to block it. And when you attempt to block it, you can feel what deadheading 9 meters of head feels like. It's good physiotherapy exercise, deadheading. Actually put your fingers over the water jet. It's good exercise. And so that is an example of a teach speech that teaches us the interplay between head and height, and also the interplay between kinetic energy and potential energy, so that there's a trade-off. As you go to the higher platforms, when you jump down, you're going to get more wallop from the water, but you get less from the water coming out. So you can see you've traded off one form of energy for another. The head decreases as you get higher, but the potential energy that you build up by climbing further up those stairs is more, so that when you drop down into the water, you'll feel more punch when you hit the water at the bottom. And so this is just a little explanation. And then I designed the steps so that they would be each 20 centimeters in height, so that you could actually jump from a variety of heights in 20 centimeter increments. So if you decide you want to jump from 4.8 meters instead of 5 meters, you just step down one stair and jump from there, or you can jump from 4.6 or 4.4 or 4.2 and so on. And so this gives you the ability to experience and understand kinetic energy, potential energy, and head pressure. And so that's one of the examples. And then there's other things here, like the internet connected Web 3.0 fountains that send packet of water across cyberspace for fun and frolic and physiotherapy. And also the hydrolophone, which is the underwater musical instrument in this hot tub here, combines a kind of wellness center or a wellness thermal bath with physiotherapy and music and fun and math and physics. And so the idea here is to combine these elements. So it's kind of following the philosophy of Albert Einstein. Albert Einstein said, "The pursuit of truth and beauty is a sphere of activity in which we are permitted to remain children all our lives." So it's this lifelong childhood sort of that Albert Einstein was onto. And so we kind of imagine a space where quantum physics and fluid mechanics come together as nature, the environment, arts, culture, society, health, wellness, innovation, therapy for the mind, body, and spirit through the universal medium of water. And so this is this was WaterHCI 2007, which we held in Copenhagen, where we sort of settled into a large water park and set up that as a research lab for about a week or so to do some fun research in the nexus of water, humans, and technology. This is WaterHCI 2011, where we brought together some First Nations musicians and with Waterfront Toronto, University of Toronto, to envision a waterfront research, fun and frolic teaching space that includes ancestral teachings. If we look historically, over on the right, there's this sort of taxonomy of water-human-computer interaction. We have the 3 taxons that Mark Matson introduced, which are swim, drink, fish. That we either go inside the water or the water goes inside us, or we separately enjoy it. And the same is true of technology. We can have type 1 cyborg wearables, type 2 cyborg implantables, or we can have the human-computer interaction in its traditional form, where the human and the computer are separate. At the bottom, I'm showing a simple example of a vessel. So the human enters the vessel and the vessel enters the water. And that's kind of shown diagrammatically. So this is kind of a border crossing taxonomy or ontology that's based on crossing boundaries or borders. Another taxonomy that another researcher suggested is the vicinity of the degrees of contact with the water. So what he said is there's 6 degrees of contact. Either you're near the water, or there's sporadic contact, like when you're in the rain, or you're on top of the water in a boat, or you're partially submerged, or you're floating, or you're underwater. And so one problem I had with this, though, is that if you're in the rain, you're actually going to get wetter or more water on you than if you're in a boat in a sunny day. So if you're on a large, like on a large cruise ship on a nice hot sunny day, you've got lots of water around you, but it doesn't have much head. So you're not really getting very wet. Whereas when you're in the rain, even a shower or something is more water than the whole ocean on you. So I suggested what we really need is the head flow taxonomy, where we have an axis from left to right that says how much water there is. Maybe you've got a glass of water on the left, and then you maybe have a bathtub, and then you go up to the whole ocean. And then going from bottom to top, we'll have a second axis, which defines how much head is present, how much pressure. So in other words, the rain is coming down with quite a bit of head pressure. So, or a shower or a garden hose spraying a spray jet or a water jet. Even though it's only a small amount of water, a water jet can really can soak through your clothes and everything because of the pressure that it's under. So in this way, we would consider two axes, one for the quantity of water or the volume of water, and the second axis for the head. And indeed, I coined the term hydrolophobic for people who are scared of pressurized water. A lot of people are not scared of gently lowering themselves into a pool, but might be frightened of the 10-meter platform where you will hit the water at about 50 kilometers an hour. So if you think about that, when you come down from a 10-meter platform, you got this pool that's about 1 million gallons of water coming at you at about 50 kilometers an hour. So it packs quite a bit of punch then. So it's kind of like voltage and amperage. If you think about it, we can often say, well, you touch a Tesla coil and it's fun because it makes your hair stand on end. And many of us who've built Tesla coils enjoy touching them because it feels kind of cool to watch your hair all stand on end and you see the sparks fly to your fingertips and everything. And it's kind of fun. It's low amperage, high voltage, so it doesn't really do much. It doesn't really hurt much. It's just kind of fun. But if that was high amperage and high voltage, you'd be dead. And likewise, you might pick up a car battery or something that's relatively low voltage, 12 volts, and you might even touch your fingers on it. A car battery might have 900 amps of cold cranking amps, start an engine, but you can actually put your fingers on it and it won't totally vaporize your skin because your skin has a high enough resistance that you don't get so much amperage. So we can think of, I'm just going to open the Lorna here, who's going to say a few words. Come on in. Say hello to Lorna. Lorna Lou. And so Lorna is going to say a few words here. So what I was saying, though, is that we've got these head and flow are separate concepts, kind of like the Thevenin and Norton equivalents of electrical engineering. You can have a great big pipe at very low pressure, perhaps, and that doesn't, if you open that up and it sprays on you, it doesn't really feel much. You just get a little bit of, you can hold it. Or you might have a small pipe at really high pressure. But if you have a large pipe at high pressure, like if you have a stormy sea and you jump into the lake, a lot of people walking along the beach, walking along a pier, say they're just not even in the water, but they're walking next to the water and a big wave. I know a big wave smashed them and broke a few ribs and knocked them over. And so that's an example where you have quite a bit of head and quite a volume, fairly high volume of water as well. So I think this model needs to be modified. The 6 degrees of water contact is lacking in that regard. And this is where we provided or proposed in the upper right-hand corner, the head flow taxonomy, head going from bottom to top and flow going from left to right. And that actually looks like a pump characteristic curve, the characteristic curve of a water pump. So this is called the head flow taxonomy. We had at the Ontario place, at the Teach Beach, we constructed an Ontario place. We kind of went through that idea of characterizing water-human computer interface in this way. And then there's a few other things. We talk about the Smart Beach project, the summary and conclusion. So this is still a work in progress. And if any of you want to join in and if any of you want to join in on this project, let us know so that we can add you to the overleaf document. Just turn off my level and give you sleep. So yeah, and Lorna is here now. Say hello, Lorna.
Hi.
And yeah, you can say a little bit about the app. So we have this swim app. So we've developed an Android app, and it can also be run an Android simulator on a desktop computer. The problem with Apple is that it's very restrictive. It's difficult to get something into the Apple ecosystem without a lot of delay. It takes time, I guess, and eventually we'll come up with an iOS version, but that's going to take time to get it into the App Store. But Android is quick and easy to deploy. So we started with the Android, and then we can, for those who don't have an Android phone, you can use a simulator. Like some of you, I'm sure most people now have access to an Android phone or know someone who has one. But in the case that you only have an iPhone, then you could also run it in the Android Studio simulator. And so this is the app here. And what it does is it gives you the sequential wave and printing machine. Let me just turn off the lights. There's a little less glare, and I'm going to dial down. Maybe I'll just go to a smaller aperture here so you can see the screen. So you can see here on the screen, there is a choice of 3 different kinds of interaction. You can look at the real part. So this is a sonar that's implemented in a smartphone. Sonar is a technology that was developed for marine navigation for boats and vessels to find their way. So sonar itself is an example of a water human computer interface. And so now what we have here is the first form of interaction, which is real sonar, where a signal is sent out and received. The second form of interaction is complex valued sonar, where the signal is sent out and we plot the real versus imaginary in the Argonne plane as a function of time. And the third is where the real and imaginary parts are plotted separately on complex sonar. So the way the app works is you select, let's say you start with real, because that's the easiest to kind of understand. And then what you'll have here is you can choose the frequency that you would like to transmit at. And so let's say we choose 5 kilohertz, 5,000 cycles per second. You know, from this menu, you can select that, and then you can, you'll get this simulator here where you can see it's going to give you the waveform that you send out, and it's like a little Fourier series. So right here, you have a sine wave that's going to be sent out or transmitted, and then you can press start, and then you can hear that. You can actually hear, can everybody hear that 5,000 cycles per second tone? Just message back to me, see if you can hear that. Yeah, okay, so everybody can hear that. Now, if you look on the screen here, it is a sequential wave and printing machine. And usually the microphone is at the bottom end of the phone here. And so if I tap on it, if you tap on it, it'll recenter it. And as I move my hand, it swims it out. You can see I'm moving my hand. And just like that radar that we showed you, does exactly the same thing. It swims out as I move my hand. So now you could point this at a growler. Growler is a small iceberg fragment. And you could get the return from the growler and then plot that out, for example. Or you could just move your hand and capture that data and plot it out. So here I'm moving my hand and you can see it swimming out my hand movement back and forth. Now, normally what you do is you keep the object stationary and move the phone. Instead of moving the object, you move the phone. Now you can see if you took a long exposure photograph of that, it's going to plot that out. So it'll swim this out. If I go to a long exposure on my camera, let's say I'm going to go to my camera quarter second. Now you can almost see, you can see that waveform. Can you all see that waveform actually plotting itself out? Can everybody see that in real-time video? Yeah, so you can see that that waveform is plotting itself out quite nicely. Because I'm using a quarter of a second. My lips are a little blurry when I'm talking because a quarter of a second is a fairly long shutter speed. But, and you can see when I move if I move around like that, everything's a little choppy, you know, or a little blurry. But the fact of the matter is that you can see that with the naked eye. You can actually see that phenomenology. So what we have in this app is a combination of a sonar, like a lock-in amplifier, signal generator, a sequential wave and printing machine, kind of all built into this app, as well as a Fourier synthesizer. The functionality of that Pascal Fourier synthesizer over here is built into the app, as well as the functionality of this cathode ray oscillograph that's swimming something out, and the functionality of a sonar, and so on. So yeah, if you want to just run through a couple of the things on that app, I'll just zoom in a little so that you can just give a quick overview, maybe, of the app.
You want a brief demo of the other two modes?
Yeah, why don't you just kind of give a brief demo? So there's two other modes. The one other mode is just real and imaginary, like if you go, and the interesting mode, I think, is the one where you've got the complex argon plane.
Oh yeah. So for this mode, we will see the.
Let me dial down. Let me go back to a long shutter speed so that you can see it, because it'll be easier to see the screen, because you can't read the screen. Otherwise, yeah, I can read that.
Okay, so at this page, we are able to adjust the buffer size and the frequency. We list some common frequencies here, and we can freely type in any frequency. And here we can see the real and the imaginary.
Yeah, if you hold it up like that, you can probably see that. Bring that into focus. Can everybody see that? Simulator, and then let's say, what if we add? Let's say we add some harmonics here. So we've got square, and then let's say we add 9 harmonics. 29. Enter.
Enter.
And then there it is. So now there's more harmonics have been added. So now you see the square was starting to take shape, but you can still see the Gibbs phenomenon present. And now that signal is a square wave comprised of 29 harmonics. If I go, let me go to some intermediate number, like say 9 harmonics. There, that looks, you can see there's 9 harmonics of a square wave. Or if I go back here, say 5 harmonics. See, there's 5, it's up to the 5th harmonic, 1, 3, and 5. So you can see there the square wave with that less harmonic. And so each of those, and then if I start with this, you can see that's
this frequency, maybe it's too low.
Too low of a frequency, probably can't actually get enough energy through the, you'll have to, depends on the size of speaker you have in your computer or phone. If it's a small speaker, you might have to choose a slightly higher frequency. Let's say 5,000 hertz. So now there's that. Now this is on the complex argon plane. So now let me go back to a slow frequency, like a quarter, or slow shutter speed like a quarter of a second here. And now you can see that we're seeing this phenomenon on the complex plane. It's going around almost in a circle or a shape, and the shape will change, of course, depending on the waveform. So eventually, if I put enough harmonics in there, it'll start to square up a little bit, and you'll see it in the complex plane what the wave shape is. So that is a fun little app that you can use for Lab5. Or, of course, you can also implement. In previous years, we had the students implement that themselves. So the students all wrote their own little program to generate the function of a lock-in amplifier to do the sonar. But in this case, we're making it a little bit easier. Make it a little bit easier for the students by providing the app. So any questions on that? And what we're going to do is we're going to present all of this in 6 days at WaterHCI. So, you know, save the date. And if you want, you're welcome to attend for the whole day. We're starting at 9:30 in the morning. There will be a music video unveiled, released that day. The lab page is not online yet, so I will post something online shortly. And 9 a.m. there'll be at 9:30 a.m. there'll be a music video released. Monique Barry is the musician, and in collaboration with filmmaker Daniel Bowman Productions. The film was shot at Ontario Place Beach, the Teach Beach, where we built the outdoor classroom, and it's shot mostly underwater. So it's a music video that was shot underwater for the most part, and it'll be unveiled or shown first. Its first live premiere will be at this WaterHCI conference in 6 days on the 30th. And then we have Waterfront Toronto, the chair of the Waterfront Toronto speaking at 10 o'clock. And then 10:30, we have the founder, director of Therme Canada, the group that's building the wellness spa at Ontario Place. And then we've got a series of talks by other notable speakers. And then any of you are welcome to contribute to the writing or to the present if you have something you want to present or some results you want to show. This is a good opportunity to kind of get yourself out into the scientific literature. So yeah, if there's any questions, let me know. And Lorna will be happy to answer questions also about the app. By the way, are any of you familiar with Android apps? Who here writes Android apps? Have any of you written an Android app before? Anyone? No one? Okay, I've done it once, prototyping, and wrote some work for a couple of years ago, wrote some for work. Okay, so that's good. So we got like, we got some familiarity with Android apps. So maybe some of you want to contribute to this project as well too. Hack away on it a little bit. I see, Puneet, you work both iOS and Android, which is good. And yeah, that's super awesome. So yeah, let's experiment with this. So I'll post something. We're going to post some radar data from the ice that we collected. We're going to go to the ice rink tomorrow and collect more data and post that as well, and give you the opportunity to analyze and play with that data a little bit, some marine radar, and also to experiment with this app and to basically have your own pocket sonar that you can use to do some ultrasound in your own home or space. So on that happy note, let us conclude this lecture, and we'll be ready to answer any questions that you have.